Boeing 77, the airplane integrated airplane information management systems, and also the X-38. This is, in fact, I have a full description of this in the 99 paper and also in my textbook. So just do a little bit advertising here. So I have a textbook that talks about all this and plus more. But obviously, the results here, the main results, it's actually beyond the textbook. It's published more recently.
Can you give us an idea of how large the specification, something like this is?
Sure. Both the Boeing and this system, we are talking about hundreds of formulas. So like 500, 600. The railroad crossing is much smaller. Okay. This one is actually a simplified version. It's about 100 formulas in RTL before conversion to the format we need, which are Clausal form, and that has more clauses.
So that's a complete spacecraft is just hundreds of formulas.
That's right. Well, this is not a complete spacecraft. This is only this module. Okay, that integrated airplane information management module. It's only a small subset, I must say, not the entire aircraft. The entire aircraft, you're talking about millions of formulas.
Right.
Okay.
But an interesting part of it.
That's right, exactly. And the part that we can get our hands on, meaning the source code. So as people in academia, as faculty members, we may not be able to get the source code so easily, especially it's a private companies, and if it's the Defense Department, it's even harder. Okay. So yeah, but even with hundreds of formulas, doing it by hand is impossible. And with conventional model checking, for this kind of thing, it's still too large because there's a time dimension in this problem. Okay, so let's see. Let's look at how we translate these formulas. We need to do some processing before we can actually analyze this using our algorithm. So first, we are going to translate these formulas with the occurrence function into something that's called Presburger arithmetic. Basically, we are replacing the occurrence function into something that's more mathematical looking, more familiar to you. And for those that have up arrow and down arrow to indicate the start and end time of the action, we use the same function name, but we use 1 and 2 to denote the beginning and the end of these actions. Okay, so that shows that these two functions are related. This shows the endpoints of that action. So that's the SP, and this is the safety property again, translated into Presburger. Now, oops. Okay, so we are not going to actually verify this directly. In fact, we are going to prove by contradiction. So we are going to encode the negation of this SP implying SA formula. So not parenthesis SP imply SA. So basically this. And the reason is, if we encode this, then we need to just find one counterexample, and the original formula is proven. Again, this is very basic logic. So you see, I do some basically this becomes this, and finally becomes this. So SP and not SA. Okay? So I'm going to encode SP and not SA in a type of graph called a constraint graph. So SP imply SA is a theorem if and only if SP and not SA is unsatisfiable. I'm proving by contradiction. So SP remains the same, but I need to negate the SA. Okay? And negating the SA, again, if you have some logic background, the for all becomes the exist here. So this gives a little bit of problem. So we need to scholemize, use scholem constant here. So scholem constant means, okay, this capital T and U means this is for a specific value, not for all. Okay. So this is called a scholem constant. And this is the form after the negation. Now, some of the less than or equal becomes greater than, and again, we do some simple arithmetic trick. You see the 60 becomes a minus 59 here. So I can use this less than or equal, because all the formulas have to be written as occurrence function plus or minus an integer less than or equal, okay, for this to work. And the reason is if we are looking for cycle, a circular path in a graph. Okay, I will show you shortly. So again, summarizing, we have original formulas, we get the Presburger formulas, and then we put into the Clausal form like this. Okay, basically each clause is a disjunction. Okay, if it's only n, then we write on separate lines. And the objective is to find positive cycles. So I haven't told you about the graph yet, but shortly. Okay, let me go to that. Okay, so this is a graph we want to build. So you create a node for each function. If the function has a Scalable constant, like here f of t, okay, I'm going to create another node. So this is kind of like a more complex graph. It's called a constraint graph. So f of t is a separate node, but it's obviously related to f of lowercase x. So I build a graph like that, and the edge has a weight. And the weight is that integer constant that is in the plus or minus in these formulas. Okay, right here. So you have either plus 45, plus 1, or minus 59. That is the weight. That's the weight on the graph. So you see minus 30, minus 15, 0 here. So now the objective is to find positive cycles in this graph. And let's see if there's any here. Okay, if you don't have positive cycles, that is bad, because we are proving by counterexample. So if you have positive cycle, we are done. If you have no positive cycles, that means you have a bug in your specification. So it's very quick. The problem is if you have a disjunction, then you need to find 2 or more cycles because of the OR. So one could be true, but the cycle could have gone to the other part. But if there are no positive cycle, you have a bug. Okay, so we have avoided using resolution, which is the standard procedure to use on the Presburger arithmetic formulas. So here, if you identify positive cycles, there's a bug. And in fact, there's a bug here. Okay. So we need to redesign, and the goal is to do this fully automatically, autonomously. Okay. So here is adding some new edges to the graph and new nodes. So this is suggested by the tool. Again, I don't really have time to go into details, but I think you get the idea. And finally, okay, this is telling you how to basically add cycles to the graph, or you transform. Okay, let me go back here. So adding cycles to the graph to create positive cycles, or maybe transforming a negative cycle into a positive one. Okay. That of course will modify existing constraint, or maybe have to create new constraint, new formulas. Okay. So this is how the system works. Obviously, the more you know about the domain, let's say this is for airplane avionics, the better, okay, the tool is going to respond. So it's going to encode domain knowledge. So there's some knowledge-based systems inside. Yeah. Of course, you can just do this blindly. Just search, around the area and see if you get a more correct specification, as I told you earlier. Because with the counting SAT, let's see, let's go back here. With the incremental counting SAT, there's a numerical value that tells you how far away you're from the correct solution, and that's why we're using that. Again, I think I'm going to skip some details here. Yeah, but you can go ahead.
So it seems to me a problem with this is if you try to fix the specification, there are many ways for you to do that.
That's right.
Right?
Yes.
So among all the possibilities, and how do you pick
right.
one that should
You pick the one that has basically the better score. So because for each of these fixes, there's a numerical score that we get from this counting SAT.
And that is from the domain knowledge?
No, that's without domain knowledge. With the domain knowledge, it's even better. So you can say this one has a higher priority, to be added.
Okay. Yeah. But without domain knowledge, then the score corresponds to what?
Basically, how far away you are from the correct SP implying SA. So let's go back here. So basically this.